Hello guys, today we're going to review how to model physical systems. We are going to consider time-invariant linear systems. That is, a time-invariant system is a system which can be described with a constant coefficient ordinary differential equation. And a linear system, the superposition principle holds. Okay? Besides the differential equation, we can describe a model using a transfer function or block diagram. And the transfer function is the relationship between the Laplace transform of the output with respect to the Laplace transform of the input. Another way to describe them are state equations, and we use analog simulation diagrams, which we will see later on the course. For modeling a physical system, we need to identify, first of all, what are going to be our parameters, our variables, and the experimental load to be used. Parameters are physical variables which are not going to change with respect to time. Variables change with respect to time, and we will need some experimental law from physics, chemistry, or other science. Let's begin modeling mechanical systems. For mechanical systems, we can consider translational and rotational systems. What do you think are going to be parameters, variables, and experimental laws for this kind of systems? Yeah, you're right. Parameters, we have mass, friction, and elasticity constant for springs. Variables are velocities, positions, and acceleration. And experimental laws are particularly second law of Newton. Let's consider now translational mechanical systems. We are going to consider the variables involved here, and they are going to be displacement as x. We are going to consider velocity, which is the first derivative of the position, meaning x dot, and acceleration, a, equals to x double dot, or second derivative of position with respect to time. In a similar way, we may consider rotational mechanical systems, and we're going to have angular displacement, angular velocity, and angular acceleration. Do remember that units for angular displacements are radians, and we measure positive angle counterclockwise. So we're going to have omega as the angular velocity to be the first derivative of theta, which is the position, and alpha, the angular acceleration, is going to be omega dot or theta double dot. The experimental law, as expected, is going to be the second law of Newton. For translational systems, we know that the force equals the mass times acceleration. Now, if several forces act over the mass m, then we need to consider the sum of all the forces acting over the mass equals to the mass times acceleration. For a rotational system, we have the second law of Newton, but in another way. We're going to have the sum of all the torques applied to certain mass is going to be equal to the inertial moment of the body times the angular acceleration. So T is a torque acting around some given axis, and J, as said, is the moment of inertia around this axis, and alpha is the angular acceleration. We are only missing the parameters, and we're going to have three basic parameters for a mechanical system. First of all, we consider inertia elements, then we're going to consider springs, and finally we're going to consider dampers. A linear spring is some element which can be deformed by an external force, such that this deformation is directly proportional to the applied force or torque, in such a way that we're going to have that the force is proportional to the position, if we are considering a translational spring, or proportional to the total displacement of the spring. That is the difference between x1 and x2. In a similar way, we may consider that the torque for a torsional spring is proportional to the total angular displacement of this spring. Next element to consider is going to be a damper. And this damper is a mechanical element that dissipates energy in form of heat. And for this case, we have that the force is proportional to the velocity. Total velocity, meaning that B, for this case, which is the viscous friction coefficient, is going to be proportional to the difference of the velocities of these couple of points, x1 and x2. Now let's see some examples. Find a mathematical model of the mass, spring, and damper system shown in figure. Please take a look here. They are asking us to consider the initial deflection of the spring. This initial deflection is named here as delta. So just imagine if you have just the spring, you have certain position of the end of the spring. Now if you hang this mass from the spring, then what you're going to have is some initial deflection here named as delta. Okay? First thing to do is to analyze the forces acting over the mass using a free body diagram. Just for this time, we're going to make a statical analysis of the system. That is, we're going to consider that the mass is not going to move at all, okay? So, we're going to consider the weight of this mass and the force of the spring acting upwards, and consider the position to be positive downwards. Then, the sum of all forces acting over the mass is, keep in mind that the force of the spring is due to the initial deflection in such a way that we have that this force is proportional to delta. Finally, initial deflection is compensated with the weight. This expression is useful if we want to know about the elasticity constant of the spring. This happens while the mass is not moving at all. That's why we call this kind of analysis a statical analysis, just in order to know that the weight is always compensated with the initial deflection. We will now consider a dynamical analysis. For the dynamical analysis, we're going to use again a free body diagram. Now we have to consider that the initial deflection of the spring is compensated with the weight. Then the only force which is going to be applied or considered is specifically the force of the spring while the mass is moving. Now we use the second law of Newton. The only force is due to the spring, which is proportional to the position. Notice that this position now is changing. That's why we use x instead of delta. Acceleration of the mass can be expressed as x double dot. Then we rearrange the terms and we finally have our mathematical model. Let us simulate the behavior of the system. For this purpose, let's consider a general second-order differential equation as follows. And now let's make a change of variables and write the same equation but as a set of two first-order differential equations. We can build a simulation diagram using integrator blocks and sum blocks. Take a look. The first equation is an integral. I mean, the integral of x2 equals to x1, right? So, and also x2 is the output of another integrator. x2 dot is a sum. We add a proportion of x1, a proportion of x2, and also u, which is the input. For the last example, we have, which is our simulation diagram. Now let us use Scilab in order to simulate this example. Once you open Scilab, in the prompt you just type xcos. Xcos is the same that Simulink for MATLAB, so it's a graphic language for simulation. And if you can see, here we have integrators and we have the sum block, we have this gain blocks also, and finally we have the oscilloscope here. So for our example, we're going to have that some blocks are going to change, of course, right? But once you have drawn this, then you can run your simulation and you're going to find the following results. As expected, the mass is going to oscillate with these behaviors here. We have the position plot, we have the velocity plot, and we call the phase plot parametric plot, where time is the parameter, and we are plotting here the position with respect, the velocity with respect to the position. Now let's see another example. They ask us to find the mathematical model of some rotor which is mounted at open over the bearings as shown in this figure. We have to assume that at t equals to 0, rotor is spinning at an angular velocity omega of 0 equals to omega 0, and we have also to assume viscous friction and no external torque is applied. So they are given us the inertia moment here, and we have to assume some viscous friction, right? So let's solve this. First of all, let us apply the second law of Newton for rotational systems. We know that the sum of all torques applied should be equal to J times omega dot, or J inertia moment times the acceleration, the angular acceleration. Note that the only torque applied is the one of the friction, which is against the movement. That's why we are considering minus b omega. Now, the equation is straightforward, obtained as J omega dot plus b omega equals to 0. In order to find solution, we can assume, or we can propose some solution, some exponential solution for the differential equation. So omega is proposed to be omega 0 times the exponential of lambda times t, in such a way that omega dot equals to omega 0 times lambda times e to the lambda t. If we substitute in the initial differential equation, then we have this equation here equals to 0, and we know that of course omega 0 times e to the lambda t cannot be equal to 0, or it's equal to 0 only when lambda tends to minus infinity. So it's no possible way to find lambda. So we use the other equation. The other equation is J lambda plus b equals to 0. We find lambda equals to minus b over j, and finally equation for the angular velocity of the rotor is omega 0 times exponential of minus b over j times t. Now let us find the mathematical model for a typical suspension of a car. We are considering now a damper, a spring, and a mass. Similarly to the first example, we use the second law of Newton, and only forces applied was minus b times x dot, which is the force due to the damper, minus k times x, which is the force due to the spring, and this is going to be equal to mass times acceleration. So the model becomes mx double dot plus bx dot plus kx equals to 0. This is the mathematical model, okay? But going a little bit further, let us assume values for the mass, the damper, and the spring, and also some initial condition in order to know how would be the behavior of this system, okay? So it is possible to solve this differential equation using Laplace transform. So first thing to do is to apply Laplace transform to both sides of the equation. Then we obtain x of s. And finally, we obtain the inverse Laplace transform of this x. So finally, we have x of t, which is the position of the mass, to be some exponential function applied to some oscillatory function here. You can see the plot in the figure. For homework, please simulate all exercises for different values of parameters. Do not consider any input so far, and please do not deliver. You can find help using this QR code. Let us do another example. Let us find the motion equation for the simple pendulum here. So we're going to have some pendulum. We have the weight, m times g. We have the length of the pendulum, and we have our variable, which is theta. Let us consider the second law of Newton for rotational systems. The only torque acting here is due to the weight, because we are not considering any viscous friction. Then we can decompose the weight vector into a couple of vectors. The perpendicular one is the only force which causes a torque. So we use this projection. Now we are missing the moment of inertia. We use the general formula to obtain the moment of inertia, and considering that the mass is not changing with respect to the length, we find this integral to be, and we use this expression in the differential equation. Notice that we have some transcendental function, sine of theta, in this differential equation. So this is a nonlinear differential equation. Then it is not possible to apply Laplace transform in order to solve this. And now we have two options. The first option would be to linearize the system and to solve this linearized system using Laplace transform. The other way is to simulate the behavior of the nonlinear system and to see only the plots. Let us first linearize the system. For this, we may consider the following limit. Then the linearized differential equation becomes, here we have the linearized system for small angles. For this system, it is possible to apply Laplace transform and to solve the system as usual. The other way to analyze the system is to make a simulation. So guys, for homework, please simulate and compare time solutions for linear and nonlinear models for this pendulum, and use Simulink or XCOS to simulate both systems, compare solutions for different initial conditions, conclude about results, and please upload to Facebook just the plot with the two solutions. Thank you. Now let us solve a little bit more complex example. Here we have a couple of masses, M1 and M2, and they are coupled with some spring here, okay? And we have some external force, and well, let's begin. First of all, let us consider a free body diagram for each one of the masses. So we have a free body diagram for mass M1 and another for mass M2. For the mass M1, we consider a moment at which the mass is a little bit below from the initial position point. Then we may consider the force of the spring number 1 going upwards and the force of the damper also going upwards. A confusion might arise here on how to consider the forces of the spring number 2. In order to solve this, we might consider the spring to be comprised or to be a strength. So for this example, let us consider the spring number 2 to be comprising. Then the spring acts with a force upwards over the mass m1 and a force going downwards over the mass m2. Then, applying second law of Newton to both free body diagrams, we're going to have for the first mass, we have minus fk1 minus fb minus fk2, which is the force of the coupling spring. For the mass m2, we're going to have f of k2 going downwards, external force f of t going downwards also, and we're going to have minus k1 x1 minus bx dot 1 minus k2 times x1 minus x2. We are considering x1 minus x2 because the spring is comprising. The only way for this spring to be comprised is that position x1 is bigger than position x2. This assumption makes positive the total displacement of the spring, and it's coherent with the negative sign of the force. I mean the force going upwards. For the mass number 2, we use the same assumption, and this is our mathematical model. Let us go now for analysis of electrical systems. For now on, I'm going to assume that you have already taken a course on electrical circuits. So I'm going to go a little bit faster. We know variables for electrical systems are going to be voltage, charge, and current, being the current the first derivative of the charge with respect to time. And we have well-known parameters here, which are resistive elements, capacitive elements, and inductive elements. The resistance can be obtained as the relationship and the voltage with respect to the current passing through the resistor, and it's measured in ohms. It's known also as the Ohm's law. The capacitance is measured in farads, and it's a relationship between the charge and the voltage. And the inductance, measured in henries, is the voltage with respect to the derivative of the current with respect to time. As experimental laws, we have the Kirchhoff's law of voltage, which is the sum of all the voltages in the circuit is exactly the same that the source of the circuit, and the current Kirchhoff's law, which is that the sum of all the currents in the node is equal to the output current. So let's do some examples. Here we have some electrical circuits having an inductance, a capacitance, and a resistor here, and a voltage source. And we need to find a mathematical model for this circuit. Let us use the Kirchhoff law for voltages. So if you can see, it's a linear circuit, and we are going to consider the voltage or differential of potential in the inductor and the voltage on the resistor and the voltage on the capacitor. The sum of these three voltages should be exactly equal to the voltage source. So we can obtain the equation for just the charge, or we can obtain the equation for just the current, or we can obtain the equation for current and charge, in such a way that it is possible to obtain an integral differential equation. But it's commonly used the differential equation for the charge. Let's go for another example here. Let's find the mathematical model for the following circuit. As you can see, we have a couple of meshes here. The first mesh contains a voltage source, some inductor, a capacitor which is coupled with the other mesh, and some resistor R1. The other mesh it has an inductor, a capacitor, and a resistor here, and of course the coupling capacitor here. For the first mesh, applying voltage Kirchhoff law, we have L1 times Q1 dot dot plus R1 times Q1 dot plus 1 over C1 times the difference of the charge of the mesh 1 and the mesh 2, meaning Q1 minus Q2. And this should be equal to the external voltage source. For the second mesh, we're going to have, in the similar way, L2 times Q2 dot dot plus R2 Q2 dot plus 1 over C2 times Q2 plus 1 over C1, which is the coupling capacitor. But this time, we are going to change the order of the charges. This is Q2 minus Q1. This is equal to 0 because we do not have any external voltage applied. Both equations are mathematical model for the system. Now let us consider another example. And for this, we are willing to obtain the transfer function of the output voltage measured from the capacitor and the input voltage here. Okay. For the solution of this example, we're going to consider complex impedances. In general case, a complex impedance is the relationship between the Laplace transform of a trans variable with respect to the Laplace transform of a pair variable. A trans variable is a variable which needs 2 points in order to be measured, like for example voltage. And a pair variable is a variable which needs only 1 point to be measured, for example, the current. So, we may find the complex impedance for a resistor being just R, the complex impedance for a capacitor being 1 over C times S, and finally, a complex impedance for the inductor is going to be L times S. Using these ideas, the circuit can be drawn as follows. And complex impedances can be treated as resistors in a typical circuit. With this in mind, it's possible to apply the voltage divisor formula. Then the transfer function becomes the complex impedance of the capacitor over the sum of all the complex impedances. Finally, we have this transfer function expressed as follows. Just in order for you to practice, guys, please do this homework. Solve every problem for mechanical and electrical systems from the textbook. Now, let us analyze how to model hydraulic systems. From basic physics courses, we know that the flow is a quantitative volume of fluid per time unit. Then this Q, which is the flow, is going to be equal to the velocity times the transversal area of the pipe. The experimental law that we are going to use is the continuity equation. So applying the mass conservation principle, we know that the flow remains the same. So if we have a pipe with different transversal areas, namely A1 and A2, with different velocities, B1 and B2, we're going to have that B1 times A1 equals to V2 times A2. Again, we're going to have three basic parameters: resistive elements, capacitive elements, and inductive elements for an hydraulic system. First, we consider the hydraulic resistance. This may be defined as a change in the differential height needed to produce a change in the flow rate. The formula for this is that R is going to be the derivative of the difference between heights with respect to the flow. This quantity is usually a constant. Then the flow through the bulb can be described as 1 over R times the difference between the heights. And this R is precisely the hydraulic resistance. This resistance is always related to a hydraulic valve. The capacitance is the change in the fluid quantity with respect to the change in height. But actually, this capacitance can be expressed as the transversal area of the tank where the fluid is contained. Now let's go for an example. Let us consider the following hydraulic system and obtain its mathematical model. We are considering some input flow, Qi, some output flow, Qo. We have a valve here with its resistance, and the capacitance of the tank is given. So, using the mass conservation law, we may consider that the water going inside the tank minus the water going outside the tank should be equal to the water which is remaining inside the tank. So if we consider this with respect to time, then we may write this equation as Qi minus Qo, which is the output flow, is going to be equal to the flow inside the tank. Flow inside the tank can be obtained multiplying the transversal area times the velocity. And for this time, this velocity can be obtained as the derivative of the height with respect to time. Considering the flow through the valve, Qo, it's going to be proportional to the height, like 1 over R times h. So finally, we have the differential equation. First order differential equation as h dot plus 1 over RC times h equals to Qi. And this is our mathematical model. The following exercise is left for homework. We have a couple of tanks, and we want to obtain the mathematical model for this system. Once we have this mathematical model, we need to find an expression to compute h1, meaning the height of the tank number 1, for every positive time. Let us consider a couple of initial conditions for H1 and H2, and parameters are given. In order to solve this problem, we have to apply mass conservation principle for tank 1 and for tank 2. Also, we need to consider a flow going from tank 1 to tank 2 through the resistance. This will lead us to have a couple of first-order differential equations, which can be easily solved using Laplace transformation. There is another homework, guys. I need you to do some self-study. It's a couple of summaries, one for thermal systems modeling and the other for pneumatic systems modeling. And also, you have to solve problems of chapter 2, but 2.6 section. Well, be free to ask me, guys. You know how to find me. Thank you very much.